The Structuring Numbers instructional sequence is designed for first grade to follow the patterning and partitioning sequence. The sequence is comprised of 3 parts, each of which is described in a group of videos. A 4th video group describes the teacher's role in implementing the sequence successfully. The material in these videos is detailed and rather dense, requiring considerable attention from the viewer. We have organized each group of videos into segments of approximately 25 minutes to facilitate viewing. Video Group 1, which describes part 1 of the sequence, is comprised of 3 segments. Here, in segment 1A, we give an overview of the entire sequence and describe the initial activities in part 1 in detail. Segments 1B and 1C provide the details of the remaining activities of Part 1. This sequence is based on using the inquiry approach to mathematics instruction that has been described in the patterning and partitioning videos. We remind teachers that the inquiry approach we advance is based on establishing the following classroom norms. Students are expected to solve problems in personally meaningful ways, to explain their thinking and reasoning to others, to listen to and attempt to make sense of others' thinking and reasoning, to ask questions and raise challenges if they do not understand or if they disagree, and to persist on personally challenging problems. An important mathematical norm is that students are expected to give explanations in terms of what is mathematically real to them. Explanations that are only about rules and procedures are not acceptable. The Structuring Numbers sequence follows the patterning and partitioning instructional sequence. In most first grade classrooms, the Structuring Numbers sequence forms the basis for math instruction for the second 9 weeks of the school year. While on the face of it, it may appear that the instructional goals of this sequence can be accomplished in less time, our experience after using it in many classrooms is that the advances in conceptual development that take place as this sequence progresses are foundational for all later work with arithmetic. And for this reason, we urge teachers to take the time necessary for children to build these essential ways of numerical reasoning. They form the foundation for fluency with numbers to 20. The instructional sequence can also be used productively in a curtailed fashion in the first 4 to 6 weeks of the second grade year. And some kindergarten teachers that use the patterning and partitioning sequence with their students introduce part 1 of the Structuring Numbers sequence at the end of the kindergarten year. The Structuring Numbers sequence focuses on numbers between 10 and 20. Specifically, it is designed to support children's development of grouping strategies for numbers to 20. A child uses a grouping strategy if he splits the numbers into groups that he recombines in efficient ways. For example, the child might reason that 8 plus 7 is 15 because I can take 2 out of the 7 and add it to the 8 to get 10, then add on the remaining 5 to get 15. As we explain in the video on the teacher's role, the sequence also contributes to children's development of thinking strategies. A child uses a thinking strategy when he uses something he just knows or has just figured out to solve the task at hand. For example, the child might say, I know that 6 plus 6 is 12, so 6 plus 7 has to be just one more. It has to be 13. In addition, this sequence supports children's development of increasingly sophisticated quantitative interpretations of additive situations. By additive situations, we mean addition tasks, subtraction tasks, missing addend tasks, and missing subtrahend tasks. The sequence is based on the scenario of a double-decker bus and makes use of a device called the arithmetic rack. Here you see an arithmetic rack. The arithmetic rack comes from the work at the Freudenthal Institute in the Netherlands, where it is called by the Dutch name Reckenrack. In the same way that the patterning and partitioning instructional sequence used the single 10 frame as a visual tool to organize and promote mental imagery for numbers to 10 based on doubles and fives. Here, the arithmetic rack is used as a way to organize quantities to 20. The structure of the rack promotes imagery for numbers to 20 around doubles, fives, and 10. The beads on the rack are movable. They can be moved from right to left and vice versa. Initially, students use their racks to solve tasks. As the sequence progresses, the rack serves as a support for mental imagery and development of number relationships that children can use as a means for reasoning, even in the absence of visual support material. Before we get into the details of the instructional activities, we will give an overview of how the sequence progresses. Here we see the learning trajectory for the sequence. A learning trajectory is a possible path that the learning of the class as a whole might take. By that, we mean the type of activities and ways of reasoning that characterize the class as a whole. For example, in this case, initially, we see the class making configurations on the rack. The activity then shifts to describing configurations in terms of fives, tens, and doubles. Another shift occurs when students' activity is characterized by reasoning in terms of groups to solve additive tasks using the rack. Next, to reasoning in terms of numerical relations to make and evaluate configurations. And finally, to reasoning purely numerically to solve additive tasks. That is, by the end of the sequence, the rack has dropped out and reasoning is purely numerical. We want to emphasize that the learning trajectory is not a description of how each individual child will progress, but rather how the class as a whole progresses. There's variability within each class, but seen as a whole, the trajectory lays out a general idea of how the learning progresses. Stated in less theoretical terms, children learn efficient ways to add and subtract numbers to 20. They learn how teen numbers relate to 10. For example, that 10 plus 3 is 13, that 16 minus 10 equals 6. They develop mental imagery for numbers to 20, so concrete materials are no longer needed. I want to explain in more detail what I mean by each of these. First, children develop efficient ways to add and subtract numbers to 20. What do we mean by efficient? In our instructional sequences, efficient always means using non-counting approaches. Counting is considered inefficient. Using non-counting methods is considered efficient. I want to remind you why that is. Non-counting approaches, such as thinking and grouping strategies, are applicable to larger numbers as well. And in this sense, they are ways of reasoning. So rather than simply learning mathematical facts, children are learning to reason mathematically. Second, children learn how teen numbers relate to 10. The number 10 is the basis of our entire number system. It plays a special role. However, when children first learn about number, there is no reason for them to treat 10 as special, except perhaps that they have 10 fingers on their hands. So part of what has to happen in children's early development of number is that they have to learn that 10 is special. Their first encounters with that come with the teen numbers and learning the relationship between the teen numbers and the numbers under 10. Sometimes we call that the n-teen theorem. Third, and finally, in the same way that we worked with patterning and partitioning to foster children's development of patterns and mental imagery for numbers to 10, in this sequence, one of the goals is that students develop mental imagery for numbers to 20. Not just any imagery, but imagery that is centered around fives, tens, and doubles. Once they have mental imagery, children can reason independently of concrete materials. The instructional sequence is comprised of 3 parts. Part 1, becoming efficient at reading the rack. This part of the sequence is about looking at the rack that shows a certain number of beads and having an efficient way to figure out the quantity shown without counting all of the beads by ones. The emphasis is on using the colors of the beads and the structure of the rack to figure out the quantity shown. Part 2, becoming efficient with adding and subtracting using grouping strategies prompted by the rack. As with the first part of this sequence, here the rack is an integral part of the tasks. First, children use it as they solve tasks. Then they no longer use the rack themselves, but the teacher provides an image of the rack to support children's reasoning. Part 3, becoming efficient at additive tasks without the rack. That is, becoming independent of the concrete material and of visual support material. Here, children solve problems in a variety of contexts and problems posed in purely numerical settings without using the rack and without having visual images of it to support their reasoning. Each of these 3 parts involves several instructional activities. The details of Part 1 are included in Video Group 1. The details of Parts 2 and 3 comprise Video Groups 2 and 3. While Part 1 of the sequence is relatively short in comparison to Part 2, it comprises a number of activities that form a gradual shift in complexity. Here we list them for your convenience. The first activity, introductory activities. Number 2, show this many people on the bus with a shift to a focus on efficiency. Activity 3, figure out how many people are on the bus when the configuration is specified, and a partner version of that activity. Activity 4, Rack Flash, and a partner version of Rack Flash. Activity 5, Rack Bingo, and Activity 6, Rack Flash Variation, and a partner version of the Rack Flash Variation. In the first several of these activities, children use their racks to complete the tasks. Then there's a shift, and students no longer use their racks, but the teacher shows or flashes images of the rack. These visual images are designed to promote children's development of mental imagery for numbers to 20 that are doubles referenced, 5 referenced, and 10 referenced. You will see this progression and shift in use of the rack as we describe the activities in detail. After we do that, we will provide a suggested timeline for how to progress through this first part of the sequence, and we will also make suggestions for how to combine activities to form productive lessons. The first instructional activity is an introductory one and is used only once. The purpose is to introduce the sequence to children. That means introducing the arithmetic rack, the underlying scenario, and the conventions of using the rack. The first step is for children to explore the rack. What do we mean by that? As with any tool or device, it is useful to begin by giving students an opportunity to touch it, look it over, move it around, and then talk about what they notice. So each child is given a rack and a few minutes of exploration time. The teacher then initiates a discussion about what children noticed. Typically, they say things about the materials used. For example, that the beads are made of wood or maybe plastic, that the beads are on 2 rods, that the beads move, that there are 2 colors of beads with some color on each rod. In our discussion here, we're going to talk about red beads and white beads. It is important that the discussion indicates talking about how many beads there are of each color and how many beads on each rod. Also, how many beads in all. As a part of the introduction to these activities, it is also necessary to introduce the underlying scenario. The scenario is that of a double-decker bus. The scenario provides a basis for posing tasks and for children's interpretation of the tasks. For this reason, it is important that the teacher takes sufficient time to make the scenario real to students. They should be able to imagine people sitting on the bus, more people getting on the bus, or people getting off the bus. In our experience, teachers typically show great creativity in how they introduce the scenario. Many show a picture of a double-decker bus and talk with the class about who has ridden on a bus like that. The important point is that the scenario becomes realistic to students and they can imagine acting within the scenario. They can imagine trying to figure out how many people are on the upper deck and how many people are on the lower deck. Their imaginary actions will form the basis for how they use the rack for reasoning. It is also important to introduce the conventions of the rack. The teacher ensures that students all place their racks on the desks in the same way so that discussions about beads and colors of beads have uniform meaning. Beads start off at the right, and the rack is placed so that the white beads are to the right of the red beads. Once the scenario is introduced, the teacher explains that the arithmetic rack will be used to keep track of the number of people on the bus, on the upper deck of the bus and on the lower deck of the bus. This is done by moving that number of beads over to the left on the two rods. For example, to show that there are 2 people on the upper deck and 6 people on the lower deck, we move the beads as shown here. It is important to emphasize that the beads show the number of people on the bus, not the people themselves. This is an important theoretical point. The rack is not a pretend bus, and the beads are not pretend people. Rather, the beads show the number of people on each deck of the bus. Why does this matter? Well, what if the beads represented people? Suppose the leftmost bead on the upper rod represented a person, say Sam, and he wanted to get off the bus. Because of the way the rack is made, we are not able to move that bead back over to the right because there's another bead in the way that would have to be moved first. In other words, Sam would not be able to get off the bus. So there would be a problem with the scenario. Another way to say it is this: the rack is not a pretend bus, but is a representation that shows quantity, not people. In this way, by using the rack, we are already moving above the scenario to focus on number, on quantity, not individual people on a bus. Having said that, in my experience, if the teacher is not careful to make this distinction between number of people and actual people, but conflates the two, the instructional sequence, nevertheless, is highly productive. I have never seen a child perplexed about Sam getting off the bus. After the initial introductory activities of exploring the rack, introducing the scenario, and establishing the conventions of the rack, the next instructional activity is to have children use their arithmetic racks to show some number of people on the bus, doing so in any way they like. This activity might be used on the first day immediately after the introductory activity, or it might be used on the second day, depending on how much time is devoted to the introduction. For example, show that there are 8 people on the bus. The children's task is to move 8 beads to the left side of the rack, in any way they choose. There's no specification of how many people are on the upper deck and how many are on the lower deck. Before we talk about what children do, I want to explain the purpose or purposes of this task. One purpose is to ensure that children understand how to use the rack and how it links to the scenario. In other words, we want to ensure that children understand the task as one of moving 8 beads from the right to the left. Another purpose is to begin to focus the discussion on the mathematical concepts of interest. We will explain what we mean by that when we look at what children do. The teacher is able to see the variety of ways that children move the beads to accomplish the task of showing that there are 8 people on the bus. Some children will move beads one at a time while counting by ones. Often, these are our least sophisticated children, perhaps some that have not yet developed concepts of composite units. Some children will move beads in groups, taking advantages of number combinations they already know. For example, by this time in the school year, many children will just know that 4 and 4 are 8, and they might move groups of 4 beads at once. For example, they might move a group of 4 beads to the left on the top and do the same on the bottom rod. Some children will move all of the red beads on one of the rods and then move 3 more beads, either on the same rod or on the other rod. These children might just know by now that 5 and 3 more make 8. Another way to say it is that what children do reflects their current conceptual understandings, in particular those understandings they developed through the patterning and partitioning sequence. Even so, since this is the first task in which children use the arithmetic rack, some children move beads one at a time, even if they already have some number combinations well in hand. After the children have moved their beads, the teacher engages the class in a discussion. The question is not, how did you move the beads, but is, how did you show that 8 people are on the bus? How many do you have shown on the top, and how many on the bottom? In other words, it's not what the children did, but what they have. The purpose of this question is to generate reflection. That's similar to what we talked about with finger patterns when we ask children, how many did you show on each hand? To answer the question, the child has to look back at the result of his actions and describe the results. The child that moves the beads while counting by ones might now have to go back and count the beads on each rod to figure out how many he showed on each deck of the bus. However, children that moved groups of beads typically use that information as they answer the question. Now here comes an important point. When children say that they moved groups of beads, say someone says that he moved 4 beads on each rod. I moved 4 on the top and 4 on the bottom. The teacher can then probe to ask, how did you know that was 4? Did you have a way to know without counting the beads by ones? The child might reply that he moved all but one of the red beads on each rod because there are 5 red in all, so he needed 1 fewer. Similarly, a child that moved all of the red beads on 1 rod and 3 more might say that he knew that moving all of the red beads shows 5. What is happening here is that the discussion is moving toward using the color groupings of the beads to describe efficient ways to figure out the quantities. So that brings us to the next point. One purpose of this task is to initiate the shift in the focus of the discussion. Initially, the discussion focuses on which beads the children use, that is, how many are on the top and how many are on the bottom, but it quickly shifts to a focus on the efficiency, that is, on descriptions based on groups of beads. That shift typically happens within the very first task posed. A major purpose of this task is to get to that shift, and for this reason, this task is used only a very few times. The teacher might pose several tasks of this type in one lesson, and then in the next lesson move to the next instructional activity in the sequence. Having said that, the teacher has to remain fully cognizant of the fact that even as the instructional sequence progresses, our least sophisticated children might, in fact will, continue to move and count beads by ones for some times. As they participate in the discussions and listen to what others say, they too, over time, will advance to using groups of beads. Remarks by the teacher such as, do you have a way to figure that out without counting? Or, can you use the color groups of the beads to help you figure that out? Are useful in that regard. This concludes video segment 1A. The next video segment 1B provides a detailed description of activities 3 and 4.